Hello everyone, my name is James and I'm here to pass you through my project, a semantic data warehouse schema for crowd sourcing the learning materials in fragile context. That is for the case of the Uganda refugee settlements. And yes, let me pass you through quickly since we already know about this. There are a lot of improvements that we had to make, a lot of adjustments. We were off topic about the implementation of the warehouse since we went and actually focus more on the part of the BAT model rather than the knowledge graph, ontology driven knowledge graph, and we corrected all that, and now we have come over to present everything that we do. As we already know the fragile context, we are talking of the Uganda refugee settlements in the areas of the rhino camps, disrupted schools and road resources, and then intermittent connectivity, which we shall look after. Crowdsourcing learning materials is more like getting all ways of gathering all the learning materials all together from different sources to make a meaningful education system uh, for these refugees, like for example photos of blackboard, scan NGO worksheets and handwritten lesson plans all being scanned, and as we already know right now, all the teachers are sharing all their materials via WhatsApp and Telegram and other social media stuff, of which these sources uh, they don't actually store most of this information up to when they are actually retrieved. Like they can store it for actually a month, but when it has been deleted from the sender's end, the information is always done. It is not being stored, and this is why this comes in. And then the traditional data warehouse stores files but cannot model, meaning context or relations, and assumes data is clean and stable. And there are very many others which we actually talk about as this. Yes, and then when we talk of what is actually happening, the reality from the design assumptions that are being made for these refugee settlements is the information according to the Ministry of Education and then the NCDC, people who actually organize this kind of curriculum for these refugees, they always assume that the information is actually structured, it is organized, but then in actual sense it is unstructured. In this way, the information there which is actually reaching them or which is actually being delivered is always not the one that has been assumed that it should be. And then the technology, they always assume that in the refugee camps there is internet connectivity, therefore everything is just going to be sourced directly online. But actually, that is the wrong way, and that is the reason why we are trying to implement this to be also offline source. And then for the uh, shuffling, yeah, here they assume that it is self-service, but then there's all we actually realize that in actual sense there's a low literacy within those areas. The literacy is too low that in a way that their staffing, in this case all the staff members there, most of them are just primary teachers actually teaching uh, who we actually assume to be the secondary students in refugee camps and other higher education. And then the management is actually, we assume that is systematic, but in actual sense it is not. Uh, the process is being assumed to be the formal process being delivered, but in actual sense it is informal. They are being taught something that is not going to help them since they are already stressed. They come from inflicted areas. And then other things are the objectives, which are institutional and survival, and among others. And from the books that we actually revised about data warehousing and the rest is Edwards, that is a scalable educational database warehouse as a service, and it is online, it is a multi-tenant Snowflake schema for academic data, maths, and then the extract transform load it uses the extract using the Haddock map reduce and the OLAP queries on Hive and HDFs. And then the results achieved here is it allows multiple universities to share a cost-effective cloud warehouse, constant time data loading regardless of file size. And then the architecture limitation is that it requires universities to upload data in a rigid SV files, which for this case, not every uh, university actually requires. This one is just a one-way format actually. Yeah, that is being left to be manually instead of just doing it and then giving it also, instead of leaving it to be on one-sided like CSV files. They are leaving other formats outside like PDF, docs. They are leaving very many formats and they're only restricting it to one. So that is a limitation. And then the data limitations on this, or the context and data limitations on this is it is only tested on the theoretical university data, no mention of handling unstructured data like PDFs, as I talk about. And then another one is the e-learn semantic model for e-learning integration. And this one, they use the models used here is the all ontology for e-learning data integration. And then the SWRL reasoning rules, that is predictive modeling and time series forecasting. And then the results achieved, it was successful semantize data from multi learning management systems, that is the Moodle, and then the open universities and fed predictive model languages models for student grade forecasting and behavior classification. And this one came along with the architectural limitations, which is the ontology must be manually designed and extended for each new data source and requires um, expertise in semantic web technologies. Reasonings can be computationally expensive. And then the context and data limitations. In this case, it is tested only on software engineering courses from one university, that is the Malaga, according to them, in Spain, and then the Open University database, and may not be regeneralized to other disciplines or institutions. And this is another one of it that we can talk about. Yes, I may not pass through all of them, but yes, these are a few other books that we actually talk about since we already talked about them in the previous video. So yes, our problem statement is the domain problem. We have domain problem and computational problem. Our domain problem comes from the education in humanitarian crisis. To be specific, here is the Uganda refugee settlements. And we understand that in Uganda, there are over 1.5 million refugees, primarily Sudanese, Somalians, Congolese, and they use these people here. Therefore, schools are frequently disrupted with the unreliable information and unorthodox system, or let me say the systems that are not actually meant for them. They're actually being taught the system that is meant for the people who are stable-minded, not the people who just came from the land where they are conflicted, they are stressed, they have a lot of trauma in them, and again, they are being pushed to learn something that is more stressful than it usually looks to be. And teachers rely on locally crude source materials, which means they actually not verified sources. And the question here, the domain problem question comes, how can fragmented crude source educational materials in Uganda refugee settlements be organized as semantically enriched and reliably retrieved by teachers operating under severe bandwidth and hardware constraints? Well, this is where we come to epistemic trust and educational resource. That is for the computational problems. The level 0 is the epistemic trust and then educational resource alignment. And then the second level is the weak supervision from crude source metadata plus the large language model assisted extraction. And then level 3 is the semantic context based retrieval and entity linking. Level 3, on the other hand, is highly unstructured multimodal educational artifacts. Most of these things we shall actually look at them when we come on this. And then in conclusion here, the relational database suffer a catastrophic schema mismatch. That is a knowledge graph infrastructure is required for this to manage the database well. The research questions and objectives here is some of the questions that actually led to us making the research and answer these problems is how can we semantically extract unstructured pedagogical entities from unstructured, noisy, crude source educational artifacts in low resource settings. And then another question that can lead to this is, how can an ontology-driven knowledge graph represent relationships between crude source materials and formal curriculum standards? And the next question follows, how can the graph neural networks provide accurate context-based retrieval under extreme graph sparsity and out of distribution conditions? And some of our objectives here is to design and evaluate an LI language model assisted semantic extraction pipeline for noisy multimodal educational context. And the rest of the objectives also follow. And this is where we come to our research contributions. We design a knowledge-driven graph, a schema for crude source educational materials, pedagogical notes using the pedagogical notes, artifact notes, and semantic edges, which we shall see later. And from this one here, we are also using the benchmark. We are benchmarking the graph model language pipeline for sparse educational graphs with uh, without of distribution evaluation 84 of. But here what it means is this: we first train the BAT for classifying as one of our models, and then after training it, we now use the BAT which we have trained for classifying to actually train the GNN model, which is actually going to help us in the knowledge-driven graph, of which we shall see from down as we continue. Yes, our methodology and the system architecture, the end-to-end system architecture for semantic search in refugee. Now, this one here is how we actually implemented it, is the semantic search. How, when we are going to search, like for example, if I'm to just enter something like photosynthesis, what books are they going to bring for me? What kind of study materials are they going to bring for me? Okay, what is it going to suggest for me based on what has been trained? So we got the data collection from the PDFs from the NCDC, and then we train them using the BAT. Okay, and then but before we train them using the BAT, we first went to we did what we call text extraction. That means from the images, from the PDF, from the videos. But for our case, it is from the images and the PDFs. But for the videos, we have not actually extracted them directly from the PDF of the NCDC. Uh, we got them outside it, and all this one here is being all converted into plain text. After being converted into plain text, we now train a BAT classifier, okay, which is actually showing us here as per now. And then the BAT classifier in this case is now going to tell us, it is going to, when we load a PDF, first of all, this is what this is going to do. It is going to operate. The text is going to be extracted and then being fed into the BAT classifier. The classifier is going to determine the common phrases. Like for example, germs are this, photosynthesis is this, germination is this. So therefore, it will know that this subject is indeed biology because it got this terms within its text, and we got it in this and such a way, and it will give its prediction accuracy based on that. And then after that is now going to be taken into the semantic understanding, whereby a user will be prompted maybe to enter something like solve this. Okay, and then now this one is going to be put into the BAT classifier, and classifier, the model which we have trained already now is going to work on it, and it is going to say this is mathematics, and it is how confident it is on this, and as its output. This is what the BAT is actually doing. It is just going to output the subject and the uh, and the and the confidence it has that, yeah, this is indeed such and such a subject. And then this is where the LLM semantic understanding comes in, which is the LLM concept extraction. Why did it say that this is indeed mathematics? It is because maybe it detected algebra from here, and then equal sign, which is this, and then addition, which is this. Okay, so it actually assumed that this equation is an algebra because it has a plus sign, equal sign, and other things. Okay, and then when it does that, this is now where we come to what we call knowledge graph. Now from the knowledge graph here, we are going to have what we call notes creation, edge creation, and then we finally find the knowledge results. Okay, the note creation in this case, it is going to take the subject, the ID, it is going to take like the ID artifact 1001, because it is going, we assume that this one is going to learn so many artifacts, so each artifact gets an ID artifact. So 001 subject, and it's going to tell us mathematics, file name, algebra, PDF. Okay, if that is what we actually uploaded. And then from there, artifact 2 is going to the concept. After artifact node, we go to the concept node. On the concept node, it is also going to have a concept ID. Okay, and then the name, algebra, and difficulty, it is going to give us moderate based on how the solution has been rendered, or based from what it learned from the book. And then the agent node, it is the user who actually uploaded this kind of uh, PDF, or maybe the notes. Okay, so this is where it is going to say trust score, and then it gives us score from the user side. And then now from the teacher, okay, this is now the age creation node. It will tell us that the artifact 1, which is the subject, okay, teaches the concept node 1. So we are understanding that the artifact 1, since it is mathematics, what concept node does it teach? Algebra. And how difficult is it? Moderate. And then verified by which user? Now it is going to tell us the user that uploaded user 001 verified artifact 1. And then now it is going to tell us the prerequisite 4. So it is going to tell us now that the concept, okay, the concept that was detected is the concept 22 is related to concept 21. Now, this literally means that if there are other PDFs there already existing, okay, and its concepts have been picked already, it is now going to say, yeah, since now these two are related, so we all tie them together under one artifact, of which we all understand is that we all file them under one artifact and they are all under one subject. So when the user goes and now search for maybe algebra, it is now going to bring artifact 1, okay, since it is the first one that we all know, and then plus other artifacts where algebra exists. So all the subjects, they are going to be displayed, and then the process continues. And then the results will be the graph, the knowledge graph, with one artifact, or with one artifact, 3 concepts and 6 edges. That now this one here I'm basing on what we actually view here, but when we are searching for it, it is going to bring more than one artifact, and then more than one concepts and more than edges, where it actually finds this coming in. And thank you for this. Yeah, now the next one is the GNN at architecture. This is now where we come in. Now this one has inputs, okay, and we have the input layer. Input layer, this is where the node features reside, okay. Node features is where we decide, it is actually, this is the model working. In this case, it is not the user working, it is the model working. It is going to receive the node features from the knowledge graph, okay, from what the knowledge graph has actually predicted and analyzed, and then here it is going to be fit as the input layer. Now from there we are going to go into layer 1, which is the site conf, and the site conf is actually more of a message passing. So message passing in this case is going to organize messages into their relevant, understandable steps, which can be literally displayed for the user in the right way, or in a way that the models actually operate with the knowledge graph, and then the user gets what is right. And then from there now it is going to output, okay, the concept. Now this is the formula that is actually existing within our, that's the formula that is existing within our writings, which we are going to see later. And then now it is going to output now the final results of the node features, okay, or the node embeddings in this case. And the node embeddings here now will be now after the layer 1 has now made all its analysis. It is now going to pass it through ReLU activation, which is going to tell us that h is equal to h max 0 to h, and now this is where the embedding will be finalized and then output as the node embeddings for every node that has been created on this end. So now the node embeddings is mostly we are just getting all the nodes that have been analyzed, put all together and then putting them so that they can easily be accessed by the user based on the site that is being made by the user. And finally, on top of this one here, my back end actually we deployed it on Google Colab because we couldn't get any other place to deploy it from. And then our front end is still on the Flutter mobile app. And this is where most of this work is going to begin. Thank you. Yes, now our dataset description, our previous dataset description, we are more focusing on the NCDC, but maybe because we were in a rush and we apologize for that. And here, the dataset, we are actually using the artifacts based on the NCDC PDFs. Well, NCDC PDFs, we use them to train the BAT model, but then when we go to the knowledge graph or the GNN model, we had to now use the BAT, which still include the PDFs from there, from NCDC, to guide us in this. And then now, the subjects covered were 25 subjects so far. Examples are there: biology, chemistry, physics, mathematics, history, geography, and among others. And then the use case is training subject classification models under supervised learning. As we can see here, our total artifacts from the 25 subjects were 108. Also what it learned. And then the total concepts were 115, and then the total agent notes were only 4, and then the total notes in total, those one being added, all the total notes after like semantic from the previous one, after the note embeddings, all became 227, and then the total semantic edges now became 561, which means that it is actually wide. We can actually cite for anything, and then we get it based on what we cite. And then the subjects covered were 25, as we talked about. That is actually the overview of our data exploratory analysis. And then when we come to the graphs representing all this, now this is our knowledge graph node distribution, the node distribution part of it. And here we can understand that our artifact nodes were 47%, and the one taking all is the concept nodes with 50.7%, and then the total nodes were this, as we saw it from our notes there. And then this is now our subject distribution in knowledge graph. Now in the knowledge graph, this one it could look the same as our previous, but in this case, this is different. So from here, this is a distribution based on the artifacts. So when we look here is the number of artifacts, and then the one with the highest number of artifacts here is art and design with 4 artifacts. And then the second is mathematics, and the list continues up to agriculture being the last. So the rest have been ignored because they have least artifacts, or they were not actually accountable for the artifacts. That's why we are only seeing this, but in actual sense, we get to understand that art and design, art all that, because when we come to the knowledge graph actually does not differentiate between metalwork, technical drawing, and other art related stuff to be individual subjects. So they all put them under artifact and design based on the notes and edges that has been getting from within the subject. Yes, this is still. Now, our results model training and validation and testing. Our model one, as I told you, was about the BAT subject classifier, which is a pre-trained bidirectional encoder representation from the transformers model fine-tuned to classify educational artifacts into 25 subject attributes. And how it works is the we input the raw text extracted from the PDFs via images via OCR, and then processing BAT encoders, that is the text, into the conceptual embeddings. And then finally, the output will be the subject, and then the confidence, as we all talked about already. Now, the role in this system is the first semantic targeting step, and it converts the raw text into the structured subject meta data before knowledge graph insertion. And the model 2 in this case is the LLM concept extraction, which is the large language model concept extraction. Now, a large language model prompted with a schema constraint generation to extract pedagogical entities from noisy unstructured artifacts. And how it works here is that the raw artifact text, possibly blurry OCR from blackboard photos, Yeah, like someone just takes a picture from the blackboard, and then prompts includes schema, constraints, and must return the target age, language, dialect, and then core concept and difficulty. Okay, so now the structured the output is going to be the structured metadata, which is the algebra, because of uh, for example, algebra, equal sign, addition. Then the mitigation in this case is the extracted entities cross-reference against cross vocabularies to prevent hallucination. And then the limitation is the extreme uh, linguistic variation, that is semantic drift risk. And then low confidence items flag for human review. And this one we are actually going to see it in different ways. What we understand by the low confidence items. Low confidence item is the one we upload the item, and then the model doesn't understand where actually this one belongs. Why? Because it is actually having text that belong to many subjects. Okay, so this one sometimes the model says not sure of the subject, so it will output that kind of message, not sure of the subject, but it will not prevent us from uploading the subject. We shall upload the subject, but it's not sure of the subject. But when the user goes and maybe search for the algebra, assume that within that subject that has been uploaded, which the model wasn't sure, it is still going to bring it among the suggestions. Okay, why? Because algebra appears in that PDF. Yes. Now, model 3 was the graph neural networks. And then what it is an inductive graph neural network that learns node representations, that is the embeddings as we have been talking about, by aggregating information from each node's local neighbor in the knowledge graph. Yeah, that is actually what I'm talking about. Each notice local neighbor. Local neighbor, now we are now understanding anyone that is actually neighboring with the what with the node that has been searched about. So it is going to bring out that. And then why there's a graph site, not CG. These are all other models like the GAT and then GCN. Now GCN is transductive. That means it cannot handle new nodes and fails as new artifacts are continuously added. And such is inductive. It generates embeddings for previously unseen nodes and then critical for dynamic refugee knowledge graph. And then GAD, on the other hand, has a higher computational cost. It is actually good, but it has a higher computational cost. It is unstable for 1 to 2 GB RAM devices, but it's a very good model that actually looked at here. And then another one is the intuition. Now here, for the intuition, uh, pool connected nodes, that is the artifact and the concept it teaches. Okay, so that means the artifact teaches a given concept. So closer is embedding space, and then push unconnected nodes further apart. The result is semantically similar materials clustered together. Now, in simple terms here, like if I'm to say pull connected nodes, pulling connected nodes is that when it takes an artifact and it takes the nodes and they are all related, okay? Like for example, this artifact has this kind of a concept, okay? It is now going to bring all these ones into embedding space, and that is when we are seeing all the output there. So when you are searching for something like photosynthesis, it is going to bring all the nodes, okay? It is all going to bring all the artifacts because photosynthesis is a concept, okay? So it is going to bring all the artifacts that are having the concepts of photosynthesis, and then it is going to display them, okay, as you are searching for more. So if there's any node that has specific photosynthesis that you're searching of, now it is now going to start sorting them one by one, eliminating them. And that's where we have the push that unconnected nodes further apart. Thank you. And yes, and then this was our GNN retrieval performance. And as performance can be, the interpretation on this case, as we can see, precise at 5, and then the value was 0.652. The direct interpretation here is the 65.2% of the top 5 retrieved artifacts are relevant. In simple terms here is when you search for photosynthesis, the top five are always the most relevant. Okay, the top 5 artifacts that display, okay, the PDFs that display first are always the most relevant, which means that is where the photosynthesis is. The rest might have maybe like something like photo and not. Okay, so down, and then the rest continues with the rest of the uh, predictions here. talking of the performance. Yes, now our model selection, of which this one we have already seen the model that I selected, or the one that we have actually been precise on. Uh, we have BAT, we have selected BAT model for training the rest of the stuff, but then the model that now we are in, that we are going to deploy, is the GNN. Well, this is now the interface for our project, the dashboard. So this is the login, and then when someone logs in, we get something like this, whereby we are getting the number of users, the resources, the total downloads, and then the model accuracy based on predictions and all that, and then the user growth analysis, and then the uh, content quality metrics, regional distribution, because these are very important for us. Like, for example, regional distribution, we need to get to know which regions are performing well, which regions are actually making use of this platform. How are they getting, whatever they are getting from it. So it is actually a very good one. And then we go to the users dashboard, whereby we get to know the number of users. And when we click on a user, we get the information of the users, where they come from, the region, what are their, how are they loading, and we have to get every information from them. And then finally, this is now the report generation. This is where we can now generate reports. Unlike the concept that we started, here we are going to have a lot of formats instead of the CSV formats for generating reports, PDFs, and then we can generate. Sorry about that, I forgot. I thought I was running it directly from the local. You see? Yes. So when we go uh, down, we can click on generate resource, and here we can actually generate them. We just select from the report type, executive summary. We can generate reports on resources, on the users, on anything, okay, on the region as well. So we can generate resource, basically what we need. That's why there's this drop down menu, of which this is just the screenshot, which means, yeah, I cannot actually show you. Yeah, and then this is just the light mode of it, literally. Let me see. Yeah, this light mode of it, showing us a bit of the graphs here. And yes, and then the resources part, we just drop down when we are searching, or probably we just search there, and then we get retrieve automatically what we need. And yes, and as we can see here, I tried to generate something and say that no anomaly is detected here, and we are literally, yes. And then the limitations of this, there was LLM, large language model extraction hallucination. And then the impact on this was that the artifacts moved to the wrong ontology nodes at some point, okay, because it wasn't getting the right nodes. It was getting confused. And then the confidence threshold, the current mitigation is the confidence threshold plus the human in the loop verification to find out that yes, this one is indeed such and such a thing. We want, by the time the user searches for something and then it hallucinates to bring other subjects which are not, the user gets to know that indeed when I search for the photosynthesis or algebra, I know what I'm looking for. Algebra, I'm looking for mathematics. So if I see anything like physics, biology there or something down after like the first five accuracy, then that means the rest are not actually what I need. And then the graph neural network is, it requires rich edges. It falls in cold start, and then the impact is the poor recommendations in the new comes. And then the manual curation for new comes is actually the mitigation in this case. And conclusion. Well, what we did is that we abandoned the rigid legacy dimensional nodes. We abandoned so many of them, like a lot of uh, warehousing schemes, like the Kimball style. And then we reconceptualize the data warehouse as an offline first semantic knowledge graph. And then another one, we use the LLM assisted data in engineering for noisy crude source content, and then apply graph representation learning for retrieval. That's what we did so far. And what we have achieved, as we saw it there, was the but this, as we first train it for classification, and then out of the distribution robustness across this, and then epidemic trust through the semantic evidence, and then the offline capable BI interface for teachers. And then there's a psychological, psychosocial support ontology. Um, Now, this one is other feature works, where since this was since this is going to be for refugee settlement mostly in this case, because this subject now this system is serving two. One, we are using it for the education, and this one for refugee settlement. Education is the current NCDC, which is another project from this. This one we are actually basing on the extending the knowledge graph to include the trauma-informed educational framework, which is critical for refugee children but absent from standard curriculum notes, and it addresses the emotional. We want to make it to address the emotional and psychological notes, not just academics. And then the multi-agent generative systems, that is transition from passive semantic retrieval to active generative intervention, which is all these are all feature works, but in our other projects we have actually already implemented it, which is not this project actually. That is our final project. And then deploy. We are now deploying here. We shall deploy, actually, let me use shall because we have not done anything. We shall deploy autonomous agents that query the graphs and then dynamically synthesize hyper-localized lesson plans adapted to individual settlement constraints. And then federated learning, which is enabling model improvement across settlements without centralizing sensitive data, and then preserve, of course, privacy while benefiting from collective learning, among others. Thank you so much. These are a few of our references, and thank you. Our acknowledgement goes to uh, a large group of people who actually aided us during the development of this system. Uh, God being the first on top of the list, and my supervisors follow, and the schools and teachers and educational stakeholders that actually participated in giving us such information on this kind of crowdsourcing platform and improving education in Uganda. Thank you so much.